this year, NVIDIA just doubled down on no, we are going to make sure that Python is a first-class citizen for all the tooling at all the levels that we develop. And so as somebody who prefers the flexibility and ease of use of Python, I've worked as a machine learning researcher where you're prototyping ideas very quickly, and then worked in developer relations where you want to stand up a demo rapidly in response to a new model release. I really like the sort of flexibility and ease of use of Python. And since it's running fast GPU code at the end, it doesn't matter if the stuff you're running on the CPU is a slow interpreted language like Python. The high pole in the tent is your GPU execution, and that's always going to be super fast. So it's exciting to me to see this commitment from the organization on making sure that those APIs are really nice.
NVIDIA's GTC conference just wrapped up, aka the Super Bowl of AI, and there is a lot to process. Big announcements on GPUs, Inference, Python for CUDA, and a whole lot of hardware and software magic that frankly can feel a bit overwhelming. That's why I'm excited to have my friend Charles Frye on the show. He's a developer advocate at Modal, a serverless GPU platform, and was on the ground floor at GTC this year. He's already shared some incredible insights with me and now is here to help us make sense of all of the key themes from GTC and what they mean for AI builders and enthusiasts. Charles, welcome to the show.
Yeah, thanks so much for having me, Manny.
Thanks again for sending some notes in advance. I thought we'd start off with this. You called this the Year of CUDA Python. Why do you think NVIDIA is doubling down on Python, and what does that mean for developers?
Yeah, the phrase Year of CUDA Python, I think I've seen it in a couple of places from the NVIDIA team themselves. It was like a theme. And what's interesting is the people focus a lot on NVIDIA's hardware because that is the thing they make that they directly sell to people. But part of what makes that hardware particularly useful isn't just that the components are really fast and things are well made or whatever, but that the software stack on top of it for making use of the hardware is actually very good. I think people will sometimes complain about NVIDIA's software stack, and I understand that because it is very complicated, but actually I would say it's more complex than it is complicated. It's like a hard problem that they're trying to solve. They've been releasing hardware for 30 years now, basically at this point, and they've had a unified interface to that hardware for 15 years or more, and they've been able to smoothly move people forward as their GPUs have gotten better and faster and more complex, with in some cases requiring no code changes, great forward compatibility. And if you work with other hardware stacks, you might find that you'll see just how much worse the software can be. And on that front, one of the biggest announcements was how much more central Python has become to that ecosystem and their investment in it. And NVIDIA has in the past, especially years ago, but even up until the last year or two, very much focused on the C and C++, very systems programming, relatively low level languages. That's been the sort of primary interface to programming the hardware. And then other people have built Python libraries on top of it. And this year, NVIDIA just doubled down on no, we are going to make sure that Python is a first-class citizen for all the tooling at all the levels that we develop. And so as somebody who prefers the flexibility and ease of use of Python, I've worked as a machine learning researcher where you're prototyping ideas very quickly, and then worked in developer relations where you want to stand up a demo rapidly in response to a new model release. I really like the sort of flexibility and ease of use of Python. And since it's running fast GPU code at the end, it doesn't matter if the stuff you're running on the CPU is a slow interpreted language like Python. The high pole in the tent is your GPU execution, and that's always going to be super fast. So it's exciting to me to see this commitment from the organization on making sure that those APIs are really nice.
Once NVIDIA's play here, is it just to expand the total group of potential users of their GPU hardware to expand accessibility? What are they angling at here?
I think part of it is a lot of people have been building these libraries. PyTorch is a very popular one. It's a Python interface to some fast lower level code, both C++ that runs on your CPU and then CUDA C++ that runs on the GPU. Lots of people have been building these things, and they've won mind share over maybe equivalent or related things offered by NVIDIA themselves. And There's also a number of projects like OpenAI's Triton is like a you write Python, you write this in this kind of like specific dialect or style. It's essentially like a little domain specific language inside of Python that then they have a compiler that will turn that into something that runs on GPUs. And people have really gotten excited about that. And there's another project people might have heard of called Thunder Kittens that people like, as you might guess from the name, it's cuddlier and friendlier. And people got excited about using that to write code to run on GPUs. And so it's like lots of other people have already been like pushing forward with this stuff. People who can move maybe a little bit faster than the manufacturer and then a $2 trillion company. And exciting to see that they've been pulled in the direction of investing more time and effort in this layer and in making these interfaces as maximally performant as possible.
That makes sense. And you also mentioned that cuTile and the new Python interface for CUTLASS both ditch C++ entirely. Is this the beginning of the end for CUDA C++?
Yeah, that's a great question. So yeah, there's two separate ones. I'll start with the one that's like less of a drop of the C++. So CUTLASS 4. So CUTLASS is one of NVIDIA's libraries for like kernel authoring, and it's designed primarily for making really fast matrix multiplications. And it's this actually very elegant and beautiful C++ library. Like I'm like a big math nerd, and they've got this both there's both like the actual linear algebra part, but they also have this like pretty cool type system if you're into that sort of thing for talking about like layouts of tensors and this very functional programming feel way of describing what happens before, what happens during, and what happens after a matrix multiplication. Very cool library, but it is C++ template metaprogramming at the bottom, which is not anybody's idea of an easy programming model or programming language. And so what they announced with CUTLASS 4 was a Python interface that wasn't just like a Python API or Python bindings, but in their claim, like a very truly Pythonic interface, like people say with PyTorch. It doesn't feel like you're exiting the like normal Python programming model to give people access to CUTLASS's capabilities from that. And in particular, like when you use raw CUTLASS, they had to do a lot more compilation work, and the with this new Python interface, they claim you can do just-in-time or JIT compilation with because there isn't as much to compile. They're only compiling tiny little nuggets and not the whole thing. The iterative compilation time as you're like working on something is, I think they said 2 orders of magnitude faster, and that's huge for sort of like an iterative debugging or performance improvement workflow. And that's very exciting to see. Still is C++ under the hood, but it's just like you don't have to write C++ to use the C++. And part of the magic and brilliance of Python as a language is how it makes it easy for you to express what you want to do with really performant code without having to inherit the strictures and other problems that come with writing in like a high performance systems language.
Gotcha. That makes sense. Is CUDA getting too hard? What's the tension between performance and accessibility here?
Yeah, that's a great question. I think what has happened over the past couple of years, there was this big change in NVIDIA GPUs with, if I remember correctly, the Ampere generation of GPUs, which if you've used an A10 or A100 GPUs, those are Ampere. The Ampere GPUs added this new hardware feature called a Tensor Core. And one Tensor Core is like as big as many CUDA cores. And one Tensor Core does a whole matrix multiplication. You just send one instruction, you get a whole matrix multiplication out the other end. And they did this to like go all in on supporting the kinds of big matrix multiplications that people do in machine learning and artificial intelligence training and inference workloads. And the cool thing about that was that it was a major contributor to the increase in performance of NVIDIA GPUs. In some ways, it was a response to people who were trying to develop like specialized chips just for neural networks. They were using some of the similar underlying technology, this systolic array approach to computing, old idea, new implementation. And so this is very cool, boosted the performance a ton, but it like steps outside of the CUDA programming model. This I think about programming one thread at a time, like each thread does some data accesses. They maybe share some information with each other and synchronize a little bit, but like they mostly operate in this very simple type of data parallelism where like you have one thread per output pixel in your image or something like that. Now it becomes, oh, a bunch of them need to, because these tensor cores are so fast, you need to like, and because they collect up a bunch of resources together to run like one big matrix multiplication, you end up doing things like, oh, I have a bunch of threads that all go in. Some of them are going and reading memory from the RAM, and then others are feeding the tensor core. Others are pulling information that the tensor core has produced and then doing stuff afterwards. And you have to, and you start to do these things where I'm like running two at the same time, and I'm like double buffering or like swapping between them, like, and the programming suddenly becomes really complicated. And so CUDA was always not anybody's idea of the easiest language to program. It feels very close to the metal, like C and C++, but it like this sort of added this whole additional complexity to the programming that has, but you need to do it if you want to get anywhere close to the peak performance of the hardware that these tensor cores offer. And these new interfaces, including cuTile, the one you asked about in a previous question, and I didn't fully explain. cuTile is designed to lift the CUDA programming model up a level so that you can talk at the level of saying, oh, I want to do a matrix multiplication, or oh, I want to do something on a bunch of things at once. And then they can be the ones, and in the compiler, they handle all of the like weirdness, buffering and asynchrony and things like that to program the tensor cores. So I think that in some ways this feels a bit like an admission that the way people were writing kernels for the last couple of years for tensor cores was unsustainable. And I'm excited. cuTile's not out yet, so haven't had a chance to take a look at it yet, but I'm excited about it as a solution to this problem.
Let's shift gears a little bit and talk about NVIDIA's hardware strategy. In Hong's keynote, he emphasized scaling up instead of scaling out. Can you explain what that means and why NVIDIA is pushing in that direction?
Yeah, this like terminology is a classic one. Back in the mid 90s, there was a lot more debate about how to build a large scale application. Like, let's take a social network. One strategy is to take, like, you have it running on a one computer, and you're like, oh no, we've got double the users, and now that this computer is about to run out of memory, like, it can't process, our database can't process requests quickly enough. One strategy is scale up, which is just buy a bigger computer. And this scale up strategy is what a lot of people from high performance computing, like where a lot of computing ideas start this like, more researchy world. They're used to like, oh yeah, just bigger computer, exaflop, yottaflop. Let's just keep making the thing bigger. And one of the interesting things about the like mid 90s to 2000s was the success of especially Google, but also a number of other organizations like Amazon that embraced scale out instead, which is like, just take that like pizza box cheap computer, exactly the same thing that somebody would buy and put in their house, and just get a bunch of them and just force all programmers to write distributed programs that run on all of them at once, that are fault tolerant when that cheap computer goes down, that split work effectively across all of these like 1,000 small computers instead of one big 1,000x computer. So that was like the story of the 90s and 2000s of like of handling scaling on the web was all about scale out. And what's interesting about what Jensen talked about in the keynote for handling large scale language model applications where you're running your own chat GPT basically, or you've got a support chat bot that needs to handle like all of your support requests, and you want to run that yourself. You don't want to just send API calls. The big thing that Jensen really hammered home in his keynote was that according to their internal benchmarking, the absolute best way to handle this is to just go for the really big, super big individual computers or individual computers. It's hard to even say what an individual computer is in the way that they're doing it. But yeah, take one server and make it as big as possible. 72 GPUs, 144 GPUs, 576 GPUs, I think was the largest that they showed. And then that's your minimum deployment unit. That's your like replica, or if you're a Kubernetes person, that's what a pod would land on. And then if you want to have more, you got to have more. You buy them 576 GPUs at a time. And claimed like once you want to operate at scale and you want to say, okay, how do I still get tokens to people as quickly as they need them? They're chatting. They want the responses quickly. oh, but I also want to be able to like process like my tokens per dollar or my tokens per second needs to be very high. Tokens per dollar needs to be high, tokens per second needs to be high. How do I keep that high? Like while also keeping the latency low and responding to people quickly. And yeah, the claim was that the Pareto frontier, the optimal way to do this was always to do like a pretty big scale up before you scale out. And wouldn't you know it, but NVIDIA is not only the producer of the individual GPU chip, the tiny little thing, but also like a whole bunch of them connected together into what's effectively a supercomputer, an exaflop scale. I think exaflop is 10 to the 24, either 10 to the 21 or 10 to the 24, I forget. It's like that's the scale of amount of like mathematical operations one single unit here can do. And given that they're the ones, one, like they build this thing, and when they sell these, they have like incredible profit margins on it, not much competition. It's like the biggest competitive advantage that they have, like the ability to construct these and sell them and in a reliable way. It's not surprising that NVIDIA would push like scale up as a narrative. I saw a talk, so I'll give you sort of two sides. One, if you read the paper from DeepSeek or the material that they've published online about their inference stack, they've been super open about how they're solving these problems. And they have their minimum deployment units are 320 plus 32. Yeah, 352 GPUs. If I remember that from their paper, like when they with just one pod or one sort of instance of DeepSeek as they deploy it of their R1 model is like over 300 GPUs. And so they're not trying to squeeze the thing down onto one node and then scale that out. And they don't have any particular reason to want to be motivated to follow NVIDIA's line here on how to scale. On the other hand, I saw a talk from a computer architect at an associated event from the GPU mode Discord, Christos S. Forget his last name, but he was like, we gotta stop with this scale up, man. It's too much. Like these computers are too big. We have to embrace the hard problem of figuring out how to do these things in a more distributed manner. So I don't have a strong intuition myself on what the right answer is to these problems. I guess the best thing I can say is this is like an important question that as a field of people offering AI inference, as engineers and technologists, we're gonna have to figure out which of these is our sort of like dominant paradigm, or in which applications, in which market segments each of them makes sense.
And is this related to the AI factory that Jensen was talking about? This whole concept of scaling up. Is he talking about the AI factory?
Yeah, I think AI factory is a little bit of a loose term that NVIDIA and Jensen in particular to throw out. I think in part because I think it's like a cultural thing. They're really a hardware designer, right? They don't run the fabs, but they have this like very actor culture, even though they're mostly designers. And that I think part of the reason it focuses on that is that it's maybe the easiest way for them to connect to a lot of their target customers, the people they're most interested in selling to. They seem to be most interested in selling to like really big enterprises that are maybe used to thinking about factories they went to Harvard Business School and they learned about the Toyota production system. So if you talk to them about factories and Andon chords and theory of constraints, like they'll get it in a way that they wouldn't if you talked in a more like a way that's more natural to a software engineer maybe, or like an AI researcher like myself who definitely wasn't thinking about factories when I was doing my PhD. So to some extent, it's like this kind of loose term that they find a way to interpret everything that they're doing through this lens. And so last year at GTC was a little different. It was a lot about digital twins and sort of other things. And oh, you would have a factory and then you would have an AI version of your factory, a simulation generative thing. And this year, the like presentation of AI Factory was oh yeah, you totally still do that, but also you buy one of these supercomputers from us, and now you have a token factory, something that like produces insights, information, um, or things that customers will pay you for, and it's a little bit more like an actual manufacturing it is a manufacturer, but of like tokens and information. And this is a very cool idea. And if you believe in this industrial revolution, or if you like this industrial revolution framing of what's going on with artificial intelligence, that it's like we're taking cognitive drudgery and making it possible for machines to do that labor in the same way that the industrial revolution took like physical drudgery and made it possible for machines to operate like that kind of versus physical labor, then like this is the obvious way that you would frame and talk about things. And I'm definitely sympathetic to that view. Yeah. But I'm also a little bit like cringing at thinking about how people who are maybe less aware of the technology and its depths than Jensen and the leadership at NVIDIA picking that term and running with it and maybe producing some not particularly insightful LinkedIn posts. But we'll see what happens.
You also mentioned that during Jensen's keynote, he threw the Hopper GPUs under the bus. What's the story there?
Yeah. This is among the most memeable moments I think of the keynote. He was talking about this. So the generations, by the way, I mentioned Tensor Cores, this new super fast matrix multiplication hardware. That was the Ampere generation. The generation after that for data center GPUs was Hopper, which if you've run on an H100 or if you read about DeepSeek trading on H80s, H800s, that's also a Hopper GPU. I've never run on the GPUs that they use, so don't know them as well. The generation after that, which is like it was announced last year, it was shipped throughout this year and is now like becoming more available. That's the Blackwell generation. And then at the keynote, they teased and talked a bit about the Rubin generation of GPUs, which will be the one after that. So another year before they're like more seriously announced, and maybe 18 months to 2 years before they ship. So the Blackwell GPUs are the new hotness. So those exaflop scale half a megawatt supercomputers we were talking about before, those are Blackwell chips. And so the like big sales event for Blackwell chips is that was big purpose of the keynote. As part of that, like when talking about this sort of Pareto frontier of the optimal way to deploy stuff and the importance of scaling out, it felt, yeah, Jensen talked himself into the point where he had to be very negative about lower compute hardware, including hardware that they are actively selling in large volume, I think, still. Certainly other people are like selling and reselling Hopper in large volumes still. He was like, yeah, there's maybe some places where you can use this hardware and it's optimal, and joked that his sales teams had to be pretty mad at him for that. So it's interesting. I think it's pretty true in that as they release this new hardware, it's classic Moore's law, but 90s Moore's law territory where it's, yeah, the hardware is a lot faster, so anything you were doing before should just get faster. The little nuance there is that you really do have to work pretty hard to get the performance that it says on the box. And so while it's true that if you're making like really good use of the hardware in both cases, then your dollar per output will be better on the Blackwell hardware. But if you just if you write something yourself, grab something off the shelf, start running things, and you end up like you spend a good amount of time waiting for your CPU to do something, or you're running just like a chat bot for one person at a time, those hardware specs, like one, the CPU's not going to get any faster just because you're on a new GPU hardware, and two, the memory is not getting as much faster. Its scaling rate is not as quick as the scaling rate for the compute. So when you're doing stuff that's a little bit more memory bound, which is commonly the case when you have a big model talking to one person at a time, maybe doing you're sending in a whole PDF and asking questions about it, those things, it's pretty hard to get to the point where the extra firepower of the latest generation actually does help. Of course, once you get to big scale, then things turn back around and you really need that extra firepower. And that's really what I think Jensen and the NVIDIA folks have in mind. But yeah, and for the latest and greatest, largest and smartest models. But I think we're seeing a lot of people still using even Ampere generation GPUs for workloads where they're using a smaller model and they don't need the full firepower per replica of these big GPUs, and I expect that to transfer over to coming generations. So I'm not canceling any Hopper reservations anytime soon.
Awesome. Let's double click into performance and tooling. Almost every talk you saw used traces or profiles. Why is performance visibility becoming such a focus in GPU programming?
Yeah, so this is like there's lots of sessions at GTC and there's a couple different tracks. There's some that are a little bit more executive, some that are a little bit more like OEM hardware-y, talking about data center build-outs. I spent most of my time in the like software engineer, like GPU programmer sessions. And so it was a lot like how to maximize throughput with and hide memory latency on CUDA, how to maximize concurrency in CUDA, or numeric formats in Blackwell. So like a lot of kind of very programming centric, software centric, performance centric talks. And they're incredibly valuable. They're available on, you can go and watch these videos on NVIDIA's website. Unfortunately, they don't land on YouTube. Maybe someday NVIDIA will, they've been getting with the times, so to speak, more and more recently on like sort of social media outreach and the sort of way they interface with their customers. So maybe someday these things will end up on YouTube. But for now, you got to go to NVIDIA on demand video and search for them. Yeah, including from past years. And they're really incredible. They're a great adjunct to the docs. The docs are very like manual style, and these talks are just these really nice. What are we even talking about here? What is our goal? And how do all these pieces fit together? So I really love that. But yeah, one of the notable things about them to me was that when describing the behavior of or when they wanted to explain a language feature or a library feature, pretty much every single talk would solve that by saying, here's one way to write the code, here's the more performant way to write the code. We'd look at it, and then maybe they would show time. They would probably show timings like, oh yeah, this takes 2 seconds, this takes 1 second, but they would generally always show like a trace. So this line of code ran, and then this line of code ran, or this function called, and it called this function, and this called this function. So these icicle or flame graphs, if you've seen those, if you use like Perfetto or Chrome tracing, those, that was how they talked about. They would like highlight, you see right here where there's this like big gap. That's because of the feature we were just talking about on the previous, like you aren't doing programmatic dependent launch. So we can't overlap the work that we would like to do in this blank spot, so the GPU is not doing anything right now. And then, oh, look at the trace on the right. That's the one where we use programmatic dependent launch. And now these things are nicely overlapped with each other. And I think what's notable about that is when you're selling performance, when you're selling like high performance computing hardware, which is basically what GPUs are, performance becomes basically part of program behavior. Like a lot of programmers and engineers are used to primarily thinking about like correctness and behavior, or like logical correctness of their program is like the thing that they test, the thing that they design around, the thing that they talk about all the time. And it's more, yeah, so you would show like sample outputs from two different versions of a program. But when performance is really what matters, it turns out that these traces to show what exactly happened become that, which is normally like internals that you intentionally hide from people. That becomes actually like the definition of the feature or the key factor of the program behavior that you have to guarantee or confirm. It's an interesting difference coming both from, I think, like a more typical software engineer and also like being an ML researcher, where like the main performance characteristic we cared about was like the quality of the models rather at the behavior of the models rather than the behavior of the hardware.
Why do you think tools like Torch Profiler and NSight systems still don't solve well for GPU debugging?
Yeah, there's a bunch of different tools that come up along the way. I think, yeah, I tend to first reach for the Torch Profiler. It's a little more comfortable and friendly to me, coming from the Python and PyTorch world. The Torch Profiler, the thing it adds on top of your generic profiling tools is being able to track stuff happening on the CPU and the GPU and to correlate them with each other. Oh, when this happened on the CPU, that triggered this behavior on the GPU. And that tool is very nice. I do know that they tried to build like higher level tooling on top of it that would like give you advice. And then TensorBoard, also like a tool from Google for ML monitoring and observability, added, oh, bring in your PyTorch trace and we'll give you advice. Like, oh, that looks low. Here's some calculated metrics from your trace, all this stuff. So they did add some of that stuff, which was nice, but some of it has been deprecated. I feel like they ran out of steam on that. And so there's two tools from NVIDIA that solve the same or similar problems. The one most similar is NSight Systems. NSight Systems in the name, it's about observing the overall system, the application that you're like doing performance debugging on. Much like the torch profiler, you're seeing stuff happening on the CPU and the GPU, and it will give you like similar information, like at a raw level, like what can you see? You see these timelines, events happening, correlating them across the CPU and GPU. They're like aggressively trying to make it like an expert systems kind of tool where it says, "Oh, I noticed Clippy style. You're not overlapping your kernels. Consider programmatic dependent launch or whatever." And then it seems like they're also working on like co-pilot tools, AI powered tools, just because it's like a classic case where these language models, even pretty small ones, are a great choice because it's mostly about like knowledge and like API details. Oh, by the way, this thing exists called programmatic dependent launch. Like I talked to a guy who had built a literal petaflop per second scale kernel in CUDA who had not heard of programmatic dependent launch. It is a relatively new feature. It's like you got to look through, you got to know what you're looking for to find it in the docs. Whereas like this thing will try and surface it for you both through like handwritten rules and heuristics, and then also combining that with this like copilot feature to make it like something you can query and chat with. So that's pretty cool, and a lot of more like enterprisey user interface level features than what you're going to get out of the Torch profiler tossed into Chrome tracing or Perfetto tracing. But neither of those solve for, they'll show you the overall system, but they are going to tell you like what's going on inside that kernel, what's going on inside when code is running on the GPU, what's happening, like how can I make it faster? So that part comes from this tool NSight compute, not systems, just the computation. And that does it, you traces it back to your source. If you turn on all the debug symbols and all this stuff, you can go all the way back to your source code and be like, okay, that corresponds to these machine level instructions, and those machine level instructions, this is the one that was causing a bunch of latency. Like GPUs are all about exposing as much work as possible for their like the hardware's internal scheduling to decide where to run stuff. And so it shows you like, oh yeah, this guy is really slowing everybody else down because like when that happens, there's only one thing for the GPU to do, and it just has to wait for bytes to come over from memory or something like that. And so it's super low level, and that's what people need to push the envelope of performance. To be clear, like I don't really need this tool that much. Like sometimes when I'm like trying to figure out just exactly what the bottleneck is when I'm trying some new tool from like a language model inference framework like VLM, or when I'm running a diffusion model like Flux with PyTorch, I might be curious, like, okay, what is going on here? But that's super low level. Oh, you should try and give a register count hint to the compiler so that you can increase your SM occupancy. That is the sort of thing that people who are building these lower level libraries that you take advantage of through PyTorch, so things like cuTLASS, the basic linear algebra subroutines that like define the map moles, or CUTLASS, they're the ones who really, they have to worry about that, and they do their tuning, and then they release a kernel. Most people, except for a small number of people who want to push the envelope of performance, don't need to go to that deep level. At a certain point, if you're really pushing it, that just is what you need. I would say the vast majority of people they're consuming PyTorch and cuDNN and cuBLAS, they are using frameworks like VLM and TensorRT-LM and SGLang. You could just use the Torch profiler and NSight systems, and that will reveal most of the bottlenecks and most of the things that you care about, and it'll help you understand the documentation of these tools to figure out how to tune them without you needing to go all the way to the compute debugging kernel layer.
You also called out Dynamo as an interesting project for distributed inference. Can you talk a little bit more about why you think that's interesting?
Yeah, so now we're switching, and if these frameworks like VLM and TRTLM are like at the middle, what we were just talking about with NSight Compute was like down at the bottom. Dynamo, we're flipping around and thinking above the level of TRTLM and VLM. So Dynamo is this neat new project from NVIDIA for distributed inference with language models. So the idea is that, contrary to the scale up mantra, actually no, that's maybe unfair. We'll say you want to run your language model, and there's kind of two parts that are very different workloads. One part is when the prompt comes in and you need to like process the prompt, which is like you run all the prompt tokens through the model at once and you generate one single next token. When you do that, you like save some information, the keys and values that are produced inside the transformer, into a key value cache KV cache. So that one is the sort of thing where like a Blackwell chip is like gonna rip, like you need a ton of extra compute power. But then once you do that, then you need to generate one token at a time, and the model needs to produce a token, then you put it back in as input, produce a token, and you only make one token at a time. So this switch actually, you go from doing a bunch of matrix times matrix stuff to doing matrix times vector stuff, and it completely changes the like kind of the characteristics of the hardware that you want. Like you might even, this is like a little sci-fi. I don't know if anybody's actually done this, but if you've heard of the Grok chip, you could plausibly want to do your prompt processing, your pre-fill step on a bunch of interconnected Blackwells, and then throw it over the line to a Grok chip to then just do the like token by token stuff. This like latency sensitive versus throughput sensitive kind of two pieces of what you're doing, the pre-fill and the decoding, or the prompt processing versus generation. And because of how different those two things are, even within this idea of, oh, scale up, don't scale out, you end up splitting things across multiple nodes. Yeah, I don't know if there's a good analogy in databases. Maybe OLTP versus OLAP kind of thing. Like it feels a little bit like that. But so you end up with these two different kind of components of your inference stack. And Dynamo is a library that they produce for managing that. Like it tells you when you need to scale up these individual components. I think it also has facilities for telling your Kubernetes autoscaler like and actually like running those autoscaling commands or interfaces. And there's a couple of interesting features in this project. I think at a base level, it is definitely interesting. Like VLM and TRTLM need to solve a bunch of lower level problems, and the distributed inference thing is something it's plausible to me that's like outside of what those frameworks need to think about and worry about. They definitely are working on trying to solve distributed inference and offer it natively inside the framework, but it's not obvious. They have so much to worry about below them in the stack that there's maybe an argument for separation of concerns there. So there's like some interesting stuff on the like sort of raw technical merits of this project. But I think the like meta conversation stuff is what was most immediately obviously interesting to me, which is one, it's like being developed on GitHub, and NVIDIA mostly actually does the development of their open source libraries on GitLab private repos and then like mirrors it onto GitHub. And so you get like a lower fidelity sense of what the development looks like, and it's harder to do you can't really do like a PR to fix stuff. It's technically open source development, but it's not like the way people think of open source development proceeding, and it's certainly not like open governance open source development. And Dynamo feels like a step in that direction of being like closer to how open source is developed at more natively open source companies. Even the big companies like Meta, Google, etc., they will develop projects like gvisor or React, like very big things that they work on. They develop them like pretty much in the open, the way lots of people are used to seeing software libraries, things in the Python ecosystem developed. And so it's like exciting to see them. Like it seems like they are recognizing that people want that. That was one of the reasons why. That's at least one of the reasons why I really like the VLLM project compared to the Tensor TLM project offered by NVIDIA. It's like way more insight into the roadmap. Like I found a bug. I checked the code. I was like, hey, I don't think you need to do this network request. They're like, you're absolutely right. They fixed it in 30 minutes. That was like a really great experience with the VLLM project. And I think they see and are recognizing and taking steps to resolve that issue that some of their software projects have, at least in this new Dynamo project. And this is a little silly, but it's a Rust project, the new for a systems programming language. I guess I'll say that. This newly popular Rust programming language, we use it a lot at Modal for building our internal systems. We like it a lot. And NVIDIA has always been a pretty hardcore C+ shop. So I'm not immediately aware of any other NVIDIA Rust projects, though I'm sure there are others, but definitely for things like announced on the keynote stage, talked about, promoted, this feels like a big step. And so excited to see them build out. This feels like part of a walk in the direction of better supporting this 6th generation systems language for programming, so that it can be used to program NVIDIA GPUs, which should be exciting to me because it means I don't have to go and learn like C++ in detail, and I can just port my Rust skills over and be able to write code directly for GPUs.
Can you tell us a little bit more about the Modal platform, and is there anything coming out of the GTC conference that makes you really excited about new features that you might make available to Modal users?
Yeah, that's a great question. Yeah, so Modal, we're a serverless computing platform designed for data, ML, and AI teams. If you're familiar with an AWS Lambda or a Google Cloud Run, we're similar to those platforms, but our goal is to be oriented to data-intensive workflows. So that's you want to run a neural network, you want to train a neural network, you want to do an analytic like batch job, you want to scrape some information from the web, anything that you want to bring a lot of compute to bear. So it's like scale-oriented serverless computing. And in order to make that work, there were lots of things that needed to come together. I think the biggest thing that's like definitional of Modal as a platform is building on cloud, especially the stuff offered by the cloud service providers. Your development cycles get really slow because they aren't optimizing for how quickly you can spin up a new thing, change your code, run it again. If you've ever worked with, maybe the worst offender on this is GitHub Actions, which isn't that similar to what we're trying to do. I guess you can use our platform for CI and you would call it out from GitHub Actions or something. But one of the biggest sins of GitHub Actions is that it's just so hard to debug. And you end up needing to create fake commits called like test in order to run stuff. And then you have these like long feedback cycles. So we like rebuilt the container stack from the ground up, custom file system, custom runtime, custom scheduler, all this stuff to make it so that you can, as quickly as possible, get your code running on the exact same hardware, exact same system that you're going to be running stuff when you are doing it in production or when you're kicking off the actual big scale job. And that's what we believe data teams really need. Like data teams aren't able to self-service serve their infrastructure. People are like have slow iteration time on model training or model inference deployments because of the difficulties of the existing solutions. And our hope is we can do that. It ends up being cheaper overall to use our platform because of how quickly we can scale up and down to match the demand that you have, and with great looking design and delightful SDK and DevX as well. Coming out of GTC, I think the biggest thing is we're super excited about this increased embrace of Python, just because Python is the primary SDK language for Modal. You can run anything you want on it, but we give you this like nice, clean developer experience through a Python SDK, so it makes it easiest to run and like debug and develop Python programs. And so we're excited about that. I think definitely came away with a feeling that increased emphasis on making profiling as easy as possible and as like smooth as possible. We already do some like tracing and profiling for CPU workloads automatically for users. You can just one click turn it on. It'd be great to have that for GPU programs. And I think, Blackwell, we expect people to want to run on them. We don't have them on the platform today because they're still just rolling out onto the cloud service providers, but we're hoping to get that out in the coming months so that, people can run their scale up larger language models and longer prompts and bigger batches on our platform.
Awesome. Charles, thanks for all of the great detail and wonderful commentary and color. Let people know how they can connect with you. Let people know how they can try out Modal.
Yeah, just head to modal.com and sign up. You get $30 a month of free compute, so you can easily run a tiny little website off of it. When I was just a user back when it was in like private beta, I ran like little websites my friends could use to generate pictures of their pets. So Accordion Space or Zoli, Renaissance painting Van Gogh or whatever. And so you could run little stuff off of it, give it a try. And then if you just try it for free, up to $30 a month. And then if you're interested in deploying something on it, reach out to us. Modal.com/Slack. You can join our Slack community. We have pretty aggressive support stance because we want to make sure people have a smooth experience that we expect them to, and to make sure we're ironing out all the kinks and details of every different type of workflow. And then you can find me in particular mostly on Twitter. That's Charles_IRL on Twitter. DMs are open. Love to hear what people are building on Modal or else otherwise. Big enthusiast for neural network technology and computers in general. Love to hear what people are working on. Those are probably some of the best places to connect. And if you follow me there, join our Slack, you'll get announcements about upcoming events IRL and online.
Awesome. Yeah, definitely give Charles a follow. And I'm a big fan of Modal. It makes it super easy to spin up GPUs all in Python, even for beginners. Definitely check out Modal. Charles, thanks very much for coming on the show. Really appreciate it.
Yeah, thanks for having me, Manny.